Hello all, my name is Kostas. I work for the company Avia.js, already gave some data about mosquito distributions. So, I'm a master student for the University of Antwerp, and this is the thesis that I did last year, and I'm doing it as an internship this year. So, why model dengue? As we can see, as the decades pass, the annual case of dengue fever increase by a lot. Next. So, population densities are increasing. Humans and goods may transfer eggs or mosquitoes themselves. Disease can be transmitted between different species, and the result is because of the easier travel, disease can spread easier. Next. So, the project that I had in mind had two main goals. One was to construct and use an epidemic model for dengue, and providing a user-friendly tool for experts to do what-if scenarios, to change parameters, pick parameters, and see how they affect the simulation results. And the second was to investigate parallelization techniques to essentially make the simulation faster in order for the tool to be pleasurable to use. Next. So I used SIR models. In a very simple term, SIR, it's like 3 connected tanks. You have water in the first tank, and these are the susceptible number of humans. And as time passes by, the number of infected starts to increase, and they start to get recovered. And you can play with these valves. It's the rates, they're different for each disease. Next, please. So this is my idea of the project. I use Cellular Automata. Cellular Automata is a grid-based technique to use difficult equations in an area and also have a really large population. So I have the layer of humans, which is real human counts, the layer of mosquitoes, which is the counts of mosquitoes, and on top of that I have climate and environmental data. Next, please. So these are some of the parameters that I used. In epidemiological paper, these parameters are known, so you can use them for dengue or West Nile fever or other diseases. Next, please. So next, again, because that's a complex equation which I used, I have the references. So I studied Nicaragua. This is how the model was split. And I used historical data to introduce infected humans on day 0. This is the distribution of mosquitoes in this area. So in cities you have more mosquitoes. And this is at the first week. I translated the infected humans into cells. So these are the cells. And as we can see, week 1, next, week 2, week 3, we can see that the spreading. We can see that the disease starts to spread to the nearby cells. Next, next, next. Okay, so for parallelization, I used an old machine. So we like video games. So video games, it's not only for showing graphics, it's for doing calculation, and it's ideal for GIS calculation. So we can use it to really speed up our models. Next, please. So this is the execution time for some specific cases, how much time it took. So I started with 800 seconds, and after using CPU and GPU graphics parallelism, I ended up with around 9 seconds. Next, please. So the conclusions. I made a model that utilizes SIR layers, which are epidemiological models. I can use birth rates, death rates. All these rates are in the literature. I also started using weighted normalization, feature scaling, to play with these valves, all these rates. So on population dynamics, I simulate that the humans travel to neighboring cells. In large scales, we shouldn't take into account the mosquito movements because they only travel 100 meters away from their birthplace. On scalability, I can simulate millions of humans and mosquitoes in just seconds rather than minutes or hours. And disease spread factors, what I found, and it's also in the literature, is that when the more mosquitoes we have in in an area where there are many humans, the faster is the spread. Next, please. So, as I said, I started with 2 to 13 minutes execution times, ended up with 3 to 9 seconds. And future steps. I didn't show any model fitting numbers because it's an ongoing project, and I will do it for the next 2 or 3 months, and I will have to present in June. So I will do parameter sweep, probably parameter swarm optimization to find the best weights, and I will use curve calibration. I will try to use DLM as well. I want also to use graph networks for train airport, ship, and travel movements of the humans. And I also want to include scenarios where you add vector control, because in reality we see seasonality in the cases. It's not that the disease can spread. People start to realize it, and you have to take it into account in your model. Next, please. And that's another model which is really complicated. It's many differential equations. I know how I can do it. So this model, this is for mosquitoes. So you have the 4 serotypes of dengue, and this is for humans, 4 serotypes of dengue. So this specific model takes into account reinfection, which is most of the models don't use it. At least the special models don't use it that much. And I think that's it.